So looking at the previous video, we were able to design a counter based on this table that we see right here, and we verified its design through the timing diagram. So we were able to verify that this was working by just looking at these numbers that we see here. So then the question is, what if we don't want to spend so much time looking at these diagrams, or we don't want to spend so much time looking at these numbers, and instead we want to develop a test bench that does the checking for us? Well, this is what I've written here. This test bench performs a general verification of our counter here. It's not the most comprehensive of test benches, but it does get the point across. I'm not going to dive too deep into this, otherwise we would be here for 30 minutes or something like that. But I will go over each of these verification phases that we see here. So let's start by looking at this first block that we have here. I call this the begin load test. And so what we're testing here is we want to make sure that the counter is loading in the value whenever the D variable and the load variable is enabled. So in this case, we're checking that Q, meaning the output, is equal to D. So if we look at our table that we described here, I'm basically checking that the Q next state is equal to D. So that's how this block here, generally works. So moving along now, here we have the begin clear test phase of the verification. And what we are checking is that we want to assert that Q is equal to the lower bound of the counter. Remember, we said that whenever the clear function is enabled, right here we have this 1, we want the output to clear to the lower bound, meaning the counter gets reset, or rather it goes back to where, where it's supposed to start from, which is the lower bound. So that's what we're checking here. So one more thing I would like to mention about each of these assertions is that if the assertion is not true, then we will get an error here. We're going to output an error. We're not going to declare, we're going to output some variables here, which perhaps explain why the error is being generated. And then we're simply going to add to a variable named flag. Now, I did declare this variable here as an integer, so I can simply just add onto it normally. So the next thing we're testing here in this block is the counting up feature here, which is this here. And so we're going to be asserting such that Q is equal to the Q previous plus 1. And if these two are equal to each other, we know that it's going to be counting up. So the important part of this block here is that Q cannot be equal to the lower bound. And if it is equal to the lower bound, then that simply means that our counter is simply initializing. So we can't make any assertions based on a previous value at that point. So then we say that Q begins at a certain value. We take a note of it and place it in the Q previous variable. And then we perform the clock. And then it's going to loop through this if statement here. And then at that point, we're checking the output. And then we're looking at the previous one, and then we're adding 1 to it. And then those two variables should be the same. And if it's not the same, then we know that there is an error going on. And we're going to just add a 1 to the flag. So if we keep moving down, similarly, we should have the countdown test, and the principle is the same. So this assertion that we see here is comparing the Q, and it's comparing it's comparing it by saying equals equals, and it's looking at Q previous minus 1. The implication here being that the Q previous should be 1 integer higher compared to the current. So by subtracting 1, we can tell that, okay, if this is true, if this is a true statement, then the counter is counting down. And so that's how it works. It's basically the same principle. Okay, so now we move along here. This testing phase, we're testing the counter so that it counts up, it pauses, and it loads. So we're testing three things at the same time. So the way we do it is we first set a for loop, and so we're looping from 0 to 25. And then as we loop through these values, we're changing the input variables for load, for enable. We're also changing load once again to 1, and then we're setting D to 5. Then we make load back to 0, and then we change load back to 1. So this basically changes our input variables a bit. So now this here, I call it begin testing assertions. So now we're testing, we're making some assertions based on the input variables here. So if this is true, then we're gonna perform this assertion like previously mentioned. This is the counting up assertion. But if this is true, that means that, let's see, actually, right here. If this is true, enable 0 and load 0, that simply means that we're pausing. So when we're in the phase where enable is equal to 0, that means the clock is paused, and load is equal to 0, so that simply means we're not loading anything. So we take a note of the current state of Q and we place it in the variable Q previously, and then we perform a clock cycle. So given this variable here, we know that the assertion Q, the current state, must be equal to the Q previous state because the counter is effectively paused. So then at that point, this is how we test to make sure that the counter is being paused. And then if you go back here to this one, we have the counter being paused, but we are loading a value into it. So now we make the assertion, okay, is Q equal to D? And if it is, then this assertion is correct, and then we say counter is being loaded with D, where D is equal to, actually this should be D, so let's fix that. D and D right here. Okay, so this is basically how it works. So now the drawback from this is that it's not quite as comprehensive because we're specifically looking at the case when we're counting up, we're pausing, and we're loading. So we are looking at 3 things at the same time, but if you remember, we have other functions such as clear, reset, and count down, but we are also making sure that the counter is within the upper bound and lower bound. So we can see that right here. We can see that in this phase as well, and then we can see it right here as well. So we are testing to make sure that the counter in general is working, but we're not doing a fully comprehensive test. But as I said, this test bench or this verification method does get the point across. So looking at the last bit of lines here, let's remember that we are keeping account of how many errors we encounter by simply adding on to the variable called flag. And by the end of it, we are also checking that flag has to be 0. So in the case that flag is equal to 0, then we simply say no errors found. However, if there is an error, we are going to get this line to execute. And then we're going to say variable flag is the amount of errors that have been found, referred to the log. Now, when I say log, I simply mean that along the command line, some of these outputs, like it's given that we had some errors. So like we should see some of these lines being generated in our outputs. And we're going to be looking at these lines. We're going to be testing our code here shortly. So when I say refer to log, I means, look back and see what the log says. Okay, so here we are back in Model Sim. So now I'm gonna compile all of this. Once again, I'm gonna simulate. You select the test bench. Okay, so if we remember, we don't have to select anything in the wave diagram because all we're doing is we are running this code. So let's see what we get. Okay, so that's good. So the first time we run it, we see that we don't have any errors. All of the tests are performed. So we see here we have a begin load test. So D is equal to 3, and this is loaded into Q. So that's good. We test the clear function. The lower bound is equal to 5. So we know that whenever the clear function is activated, Q should be equal to the lower bound, right? Obviously, that's what we said here. And then similarly, we have the begin counting up test. So we know that when we're counting up from the very beginning, we have to make a statement and saying, okay, the counter is starting from a certain value. This here, it's 4, and then it's going to be counting up. So then, since we're not making any assertions here, we simply state where it's starting from. And then 4 is, and then when we're in this stage here, 4 is simply the previous stage, and then 5 would be the current state. So this looks good. We keep going. So now we are in the phase where we're testing count up, pause, and load. So first we begin with 2. We count up to 6. The counter is paused, so it's paused at 7. So we're making sure that the queue previous is equal to the current queue, and they are. And then we're checking to see if the output is being loaded in with the value D, right? So then D here is equal to 5, and then Q is equal to 5. So that's good. So we don't get any errors here. And then it goes back to counting up. So then it goes from 5 to 6, 6 to 7, all the way to 12. And then when it reaches the upper bound, we look here, we set the upper bound to 13. So let's take a look. Yeah, right there. So what that means is, okay, it's going to go back to the lower bound too. And then all the tests are finalized, and then no errors are found. So this is a way of streamlining the verification process. So, but I would like to see some other outputs. So I'm going to go back to the original code for the counter, and I'm going to change a couple of things. So rather than saying rnext, okay, so let's look at this line here. If clear is equal to 1, that means that rnext is going to be equal to the lower bound. So what if I just change this to 0? Let's see what happens in the code. Okay, so now I've compiled the counter here, and we said that rnext is equal to 0 instead of lower bound. So let's just compile this again. Let's start the simulation. Testbench. All right, and let's run it. Okay, so then it says I have 7 errors. Well, that's expected because the clear is making the rnext state go to 0 rather than the lower bound. So let's see where we have these errors. Okay, so right here we can see that it's telling us it's not counting up. The queue previous state is equal to 14 and the queue current state is 0. So that makes sense. Well, it turns out that at this point it's also out of bounds. So then we have a double error here. Counter is out of bounds. So then that's already 2 errors. So, and then we're going to see a similar situation where the queue previous state hasn't even been assigned a variable yet, and it's giving me an error because we have nothing for queue previous. And not only that, but the counter is out of bounds. And as it should be, because we set the rnext state to 0. So that's how we get out the 7 variables. And then in the clear test, we see that the lower bound in this instant was 5, but it's not equal to 0. It's not equal to the what's in the output. So that's that generates an error. Okay, so I've changed rnext. In the case that clear is 1, rnext is equal to lb, so it's back to where it's supposed to be. But let's say I want to mess with the counter. So rather than counting up, right, because the enable is on and the up down is on. So what that means is we're going to be counting up here. So what happens if, rather than counting up, it's going to be counting down. So let's see what sort of errors you get with that. So let's compile all. Simulate. Start simulation. Okay, and then we're going to run it here. So 54 errors, so that turns out to generate a lot of errors here. So one of the things that we'll notice is that not only does it, when it count up, so not only does it not do that, but it's actually counting backwards. And in that case, it's at the same time, it's going out of bounds, right? So then immediately we can see that it's going out of bounds and it's not counting up. So that's why we have so many errors now. So as you can see, this is quite a good way of testing this counter here. So it's like we're getting errors for two reasons now. By simply changing, by simply having this wrong sign here, we're getting errors for two reasons. Okay, so let's see what happens if I change some other stuff. Okay, so I want to change this back to what's it's supposed to be plus, but let's say instead of counting down, counting up is going to be when this is, you know, when the UD is 0, that means it's supposed to count down, right? But instead I'm going to say, okay, let's just make it count up instead. Let's see what this looks like. And if you go back to the test bench, there's only one instance in which we're testing counting up. Or I mean counting down, which is this block right here. Actually, let's go back to the VS Code here. Yeah, you see here? This is the only instance in which we're testing the counting down. So we should see a little bit less errors compared to the 54. So let's go ahead and compile it. I think we already did. And then we simulate it. So it starts simulation. Test bench. Okay, and then we run it. Okay, so this time we only have 9 errors. So let's see where it is. And surprise, surprise, it's the stage in which we're counting down, right? So this is basically what we expect. It says here, we're not counting down, not counting down, not counting down. And interestingly here, since if you look back at the test bench, upper bound and lower bounds are simply 15 and 0, so there's no way that we can be out of bounds, right? Because we're only dealing with 4 bits here. So it makes sense that we don't have any errors in terms of, going out of bounds. Okay, so then I'm going to fix this. I'm going to put this back to negative. But then here, we're going to make something interesting. When it's supposed to pause, I'm actually going to make it count up. Right? So this is completely, I'm doing something that the test bench is not expecting. Or rather, it's expecting anything. It's just going to give me an error. So let's go ahead and compile all. And let's do simulate, start simulation. Let's do the test bench. So now, let's see. When am I pausing it? I believe I'm only pausing it if we go back here. Yeah, the only time that I'm pausing it, it's going to be in this block here. So this is the only block that I should get errors. So let's see. So the enable is 0, so that means it's pausing, right? But for how long is it pausing? That's the question. So we're basically pausing from 5 to 8. So what is that? That's 5, 6, 7, 8. So that's 4 cycles in the code. So we should see 4 errors then. So let's go ahead and run it. Okay, right there. So we see 4 errors. And then if we scroll up, we see that counter has not been paused. Why? Because the Q previous is equal to 7 and the current is equal to 8. So that means it's counting up, right? Well, that's because I put this 1 here, this plus 1. So this makes sense. So the counter has not been paused, has not been paused, has not been paused, has not been paused 4 times, right? It's 4 cycles. So it gives me the 4 errors. Everywhere else is fine because we're not testing the pause anywhere else other than the last block. So this works quite nicely. Okay, and just to sort of, bring this, full circle, I'm going to just take out everything, take out all the errors, and this is the code in the state that it's supposed to be. I'm going to compile it once again. I'm going to start simulation. I select Testbench. So in this one, obviously, I don't expect to get any errors because now this code is working just fine. So let's run it. And there it is, see? no errors found. So as you can see, we just tested this code and we tested it quite, pretty quickly. We didn't even have to look at the timing diagram. So that's really the benefit of developing a nice test bench that can test your circuit. And then you can make a very general test bench for more comprehensive testing and verification.